a pleasure for me to be here. The presentation I'm going to give you is about increasing food production with the perspective of a global scale analysis and through the lens of water sustainability. So one of the main challenges we will have to face nowadays and in the next future is to see the very fast growing population expected to be 10 billion people in 2050. This population is demanding for 60% additional food and energy that translates in an additional 20% in water withdrawal and 33% in agricultural area. So a competition could arise because the lack of natural resources between the energy sector and the food sector. But other challenges are arising because we have to eradicate also malnutrition that has to be intended as undernutrition, micronutrient deficiency, but also as overnutrition. All of these type of malnutrition in turn are able to determine the so-called food-related disease. In addition to that, we have that some countries are becoming more and more affluent, so they are following the very famous Venice law, especially for our colleagues, the car economists, and so they are increasing meat consumption, sometimes overconsumption in the meat consumption. This could be a problem not only for the health, but also for the environment, because it translates in overpressuring natural resources, especially water. Then, what we are observing in the last decades is an increase of the emerging infectious diseases, especially from zoonotic origin, and they are strictly associated to an unsustainable land use change, especially an unsustainable land use change due to the food sector, to the agricultural sector. So the question we have now is if we can feed a future population of 10 billion people with an healthy diet, but also with a sustainable and healthy diet. That is a diet within the so-called planetary boundaries. If we look to the history of food security to learn how it was done in the past, we see that in the 18th century, Thomas Malthus analyzed the demographic growth and the availability of natural resources for feeding the population that was growing at that time. And what he discovered was that in what it was for him, the long run, the natural resources would be not enough to feed the humanity. Malthus was disattended. We didn't have the so-called Malthusian catastrophe, and it was because we had technological innovations that allow humanity to increase food production. And we increased food production at a point that food security was not longer a problem of food availability, but of food access, as Amartya Sen noticed in his essay, Poverty and Famine. But now the question is, to what extent is current food production sustainable? And do we have enough water to feed the humanity sustainably in the future? And so the question, how many people can the planet feed, is still relevant. If we look to how we can increase food production, the two main strategies we know are the agriculture intensification and the agriculture extensification. Agricultural intensification means to close the agricultural yield gap on the underperforming croplands. And we usually do that through the so-called agricultural inputs that are water, through irrigation, and fertilizers mainly. And agricultural extensification means the expansion of the cultivated area. And both these two strategies have some impacts, both social and environmental, because the agricultural intensification could imply the transition to commercial agriculture, the loss of livelihoods, water resources depletion, and land degradation. From the other hand, the agricultural intensification can produce land use change, deforestation, biodiversity losses. Usually, ecologists advocate for intensification rather than extensification. The reason why, because they say intensification avoids habitat destruction. So what we did was to try to calculate the amount of people it is possible to feed through intensification at global scale. So through an agro-hydrological model, and I don't want to go in the math of the model, we build the model and we run the model, and the results are here reported. But at the end of the story, it is possible through intensification produce additional food able to feed additional 4 billion people with respect to the population we are now. So we can say, we are okay now. But the question now is, but do we have the natural resources to sustainably feed this additional number of people? Or are we running out of natural resources to sustainably meet food and also we will see energy needs of the future population? And if we look from a water lens, a water sustainability lens, what we see is that in our planet, we already have hotspots of unsustainable water use. We have hotspots in the United States. We have hotspots of unsustainable water use in India. We have here, we have also in China and in other parts of our planet. And if we look to the state of agriculture, what we see is that the 77% of agriculture in our planet is rain-fed, and the 23% is currently irrigated. But going more in depth, we see that about from the 11 to the 16% of the currently irrigated agriculture is unsustainable irrigated. And if we look more in depth on the other agriculture, we see that only the 24% of the rain-fed agriculture doesn't need of irrigation. Only the 24% of croplands is not needed irrigation because rainfall is enough to feed the crop water requirement. Then we have that from 28 to 38% of the croplands we have now rain-fed are in the so-called physical water scarcity condition, meaning that there is no water there for making a sustainable irrigation. Then, from the 15 to the 25% of the croplands needing irrigation are located in places affected by economic water scarcity, meaning that there is water, but what we lack there are the hydraulic infrastructures for providing water in a sustainable way. And so those are the croplands that it is possible to irrigate in a sustainable way. So repeating our calculation, what we discovered is that the additional 4 billion people that it is possible to feed through intensification, they decreased at first to 2.8 billion people, considering to irrigate only the croplands where it is possible to do that in a sustainable way, and they decrease to 1.8 if we think to eliminate unsustainable irrigation where it currently is. And so it is apparent that it is not possible in the future to deal with intensification to feed the humanity. Here, I reported the number of the irrigated lands and also the water needed in terms of volume. And here, I want to show you what will happen due to climate change. So we use the projections of climate change, and we consider both 3 degrees increase in terms of temperature and 1.5 increase in terms of temperature. The results are very similar, so I reported just the 3 degrees, the increase of 3 degrees. And what you can see here is that in climate change scenario, there are additional croplands needing of irrigation. And you can see here where they are located by country. But in addition to that, we have to consider that croplands that are currently in water scarcity condition, and they need to be irrigated not all the year long, but maybe for 2 months, 3 months. During the thanks to the climate change, they become more dependent on irrigation on annual scale. And it translates from an engineering point of view on the fact that we need to increase water storages because we have to store more water if the water scarcity lasts for more months that we have now. And this is an additional problem we have to face in addition to the additional land we have to irrigate. Close to this, we have another problem to take in consideration. Even if there are, as we have seen, croplands and croplands that can be where the intensification can be done because they are at the moment underperforming, we have to consider beside the environmental impacts they can have due to the irrigation, especially if it is not sustainable, we have to consider also social impacts. In the last 15 years, we are observing a phenomenon called large-scale land acquisition, sometimes also called land grabbing. That means that large tracts of land, and when I'm talking about large tracts, I'm talking about hundreds of hectares of land, are acquired by sometimes foreign investors, foreign governments, multinationals, and so on. And here we have the network of the large-scale land acquisitions. Up to now, around 45, 50 million hectares have been acquired on a global scale, meaning that, just to give you an idea, that the total acquired land is more than 3 times the area of Portugal. And because those land usually are acquired for agriculture, together with land there is water acquisition. And if you measure the water, if you calculate the water needed to grow crops or for livestock on those lands, you discover that it's on the order of magnitude of 500 million cubic meters. That it is a very huge, sorry, but I am Italian, and so I translated this number in the volume of our measure lake, and it is 10 times the volume of the Garda Lake. I don't know if you know, but just to give you an idea, you can make the calculation with something that is more familiar for you. And The problem of these phenomenon are, as we said before, can be environmental, but also can be social, because associated to this large scale and acquisition, there is the dispossession of the land from the previous users. And usually those acquisitions happen in countries, in places highly affected by malnutrition. And because land, water, at the end of the story means food, malnutrition can increase. But also, if we look to what happened from a very, very hydrological point of view, what we can do, and this is an exercise we did for Sub-Saharan Africa. In Sub-Saharan Africa, about 210 cubic kilometers of water per year are associated to this phenomenon. And so this appropriation of water can be felt not only from people living nearby the land deal, but if you look here, we have what happened from an hydrological point of view. If you take water in one place and you look to what happened downstream. So in the place where you see the number is the place where the land is located, where it is located the large scale land acquisition. And so there it is taken water for agriculture. And we see the propagation of the effect in terms of water scarcity from the place where water is taken downstream and downslope. So what we see is that the impact of upstream water appropriation by large-scale and acquisition can limit present and future agriculture development opportunities, while also affecting pastoralist communities in the area where this water scarcity increases. Then, I have 3 minutes. Additional challenges are due to the use of water by the energy sector. In this scenario that is provided by the International Agency of Energy Agency, we see the projection in 2030 regarding the water used for energy, and in particular for the green energy transition. So you see here that biofuel is in the scenarios for the 2030 is 4 times uses 4 times the water used in 2016. And so it is clear that a competition for water can arise between the food sector and the energy sector. And the reason why this competition arises is because because the food sector and the energy sector are strictly linked in the so-called nexus. Nexus means that water system means that food system and energy system based on the same pool of natural resources. So meaning that if one sector uses natural resources in an unsustainable way, can prevent the meeting of the challenge, in this case of feeding humanity by the food sector. And we have to pay a lot of attention on this. And we have to pay attention also to strategies put in place for example, for decreasing the effect of climate change. If we look to the 2 projects regarding the restoration in the tropics, and if we don't look to the hydrology behind this problem, we see just the pros, and the pros are many, of course, because they help fighting climate change by stopping carbon dioxide, they prevent land degradation, they improve microclimate, and so on. But when we look to the water used by trees, because those restoration implies the planting of trees, and trees use water, what we see is that the land the areas potentially available for tree planting are in arid and semi-arid areas concerning Africa and Asia, and in South America and part of Asia are in humid regions. When you consider to plant those trees, what you see, and we did this exercise, what you see is the yearly water scarcity induced by tree planting would affect the 77% of the feasible net restoration area in Oceania and South America that are the area that are humid, so the most suitable. If you look to what happened planting trees in Africa and in the part of Asia more affected by water scarcity, you see that in the 92% and in the 94% respectively in Asia and Africa, they undergo to those land undergo to water scarcity conditions. So you see here that also strategies aim to mitigate carbon dioxide can produce situation of water scarcity and so competition again with the sector of agriculture. So just to conclude, I want to say that we still have to prove Malthus wrong, because if we look to the sustainability, if we look to a sustainable agriculture production, what we see is that presently we are producing food in not sustainable way, so treating the environment, the health, and also the future of the humanity. So what we can do? What we can do is to move from intensification to sustainable intensification, and to keep in mind that one strategy is not enough. We have to put in place more than one strategy, because one strategy, if it is done in a sustainable way, it is not able to feed the humanity for the future. And then, as a colleague before me said before, we have to look not only to produce more food, but also to reduce the demand of food. And it can be done by reducing waste, because reducing waste of food means reducing the natural resources needed to produce that food. But then it is very important to change our diet, because the water needed to produce food is not the same for every type of food. In particular, there are some type of food items needing very water intensive, like for example animal food. And then we need of a circular economy of food. And concluding here, the last slide is just the conclusion.
So may I suggest that I'm going to, while the other speakers get here and sit around the table, I will get just two clarification questions for Cristina. So clarification with no comments, just, can you clarify?
Yeah, sorry, I took...
No. It's just that it's very difficult to make questions just 5 minutes in each. So while the speakers come up, if you don't mind, so clarification questions. Is a clarification question? No. So okay, here one and two. And while the other speakers, please, Slim and Michael, if you want, in the meanwhile, to sit here while we get the questions.
Thank you so much, Cristina, for a great presentation. I was just wondering whether you put a cap on the available supply. For example, do you consider groundwater as well in your model simulations? And, as we are depleting the aquifers, the cost of extractions goes up. I'm just wondering whether these are considered.
Thank you very much for this question. When we repeat the calculation, passing for the additional 4 billion people to the 1.6, it was because we considered to put a cap on groundwater and to consider also the environmental flows, because for surface flow, they are very, very important. And so the sustainability, we control the sustainability in this way. Thank you. So I forgot to tell that. Yeah. The other one.
Thank you, Cristina, for your talk. And I have just one question. have you considered or look at virtual water trades
Yeah,
and
of course.
green and blue water trades and
Yeah,
import
yeah,
of food?
Work a lot on virtual water trade. What we calculated in the exercise I show you is the potential you have in increasing the agricultural yield in the underperforming croplands. Then once you produce crops, you produce food in those land, those crops can be traded wherever you want. But in any case, you have to produce there, and then they can be traded. In any case, virtual water comes later, before you have to produce, and you can produce additional crops, additional food, and this in a place where it is possible, and then you can trade that. Yeah, this is an exercise to see where it is possible to do that and how much water you need. Yeah, and if I may add something in one of the strategies that I couldn't show you, but in a strategy for sustainable intensification, one of the strategies is to plant the right crop in the right place. So it means that you plant the right crop where you can give to the crop more green water than blue water. So where the precipitation regime is more or less, if not optimal, but good for growing that type of plant. And in this exercise, you can see that you can save a lot of blue water, producing maybe a little bit more of what we are producing now. But in any case, you save water, and that it is very, very important.